Good morning, ma'am. My name is Saipur from Computer Science and Engineering. Today, my subject object-oriented software engineering. Today, my topic is the smart agriculture system. Introduction to smart agriculture. Smart agriculture uses digital technologies to optimize farming practices and increase crop yields sustainable. It integrates sensor, actors, data analytics, and automated control systems into a unified farm management platform. The goal is to enable precision farming by monitoring environmental conditions and plant health in real time. Object-oriented software engineering provides the ideal framework to model and manage the complexity of such systems. Next, core components of a smart agriculture system. Sensors collect real-time data on soil moisture, temperature, humidity, intensity, and nutrient levels. Actors perform physical actions like opening irrigation values, acting fans, or dispensing fertilizers. User interfaces allows farmers to monitor farm status, receive alerts, and manually override automated decision. Next, object-oriented design principle applied. Encapsulations hides internal details of components like sensor or irrigation pump, exposing only necessary interfaces. Inheritance allows specialized classes such as soil moisturances to extend a base sensor class with shared functionality. Abstraction simplifies complex hardware interactions by defining high-level operations like read data or activate. These principles promote modularity, reusability, and SGS maintenance across evolving agriculture systems. Class diagram. Key entities in the system. The farms class represent the overall agriculture environment and contains multiple zones or plots. Each zone manages its own set of sensors, actors, and crop types with specific growth requirements. Accurate is another abstract class implemented by device such as water pump and ventilation fan. A data logger class records all sensor regarding and accurate events for analysis and audit purpose. Next, use case automated irrigation. When soil moisture drop below a threshold, the system detects the condition via soil moisture sensors. The irrigation controller services the low moisture alert and evaluate whether watering is needed based on crop type and weather forecasts. After irrigation, the system logs the event and updates the moisture level until it reaches the optimal range. Farmers receive a notification confirming the action and can review historical irrigation patterns. Data flow and system aggregation. Sensor continuously stream data to a central gateway using lightweight measuring protocols. The gateway aggregates and forwards data to a cloud-based or on-premise server for processing. A rule engine evaluates including and incoming data against predefined thresholds are and triggers corresponding actions. Next, design patterns is smart agriculture software. The observe pattern lets sensor notify the controller when readings change, enabling reactive behavior. The strategy pattern allows switching between different irrigation algorithms based on crop or season. The factory pattern creates sensor or accurate incentives dynamically based on configuration files. This pattern enhances flexibility, scalability, and testability of the software architecture. Challenges is system integration. Heterogeneous devices from different manufacturers may use incompatible communication protocols. Real-time responsiveness is circular delays in sensor to accurate loops can harm crop health. Power constraints in remote field required energy, efficient hardware and low power communication methods. System reliability is virtual failures in automation cloud lead to crop loss or resource overuse. Scalability and modularity consideration. The system should support adding new zones, sensors or accurates without rewriting core logic. Modular design allows independent development and testing of components like weather integration or pest distillation. Configuration files define device types and thresholds, making the system adaptable to various crop and climates. User interface and farmer interactions. A responsive web dashboard displays real-time sensor data, system status, and historical threads in chapters. Mobile apps provide push notifications for critical alerts such as equipment failures or extreme weather. Role-based access ensure only authorized personnel can modify system settings or view sensitive data. Intensive maps show zone-specific conditions, helping farmers make localized decision quickly. Next, testing and validation strategies. Until uh, testing, verify individual components like sensor, persons, a or accurate drivers in isolation. Integration tests ensure sensors, controllers, and databases work together quality under simulated conditions. Fault injections tests evaluate how to system handle sensor failures, network outages, or power loss. Case study implementation in a tomato greenhouse. A smart system was deployed in a 2 hectare greenhouse growing tomatoes using hydroponics, soil moisture, pH temperature, and CO2 sensors provided continuous environmental monitoring. Over 6 months, water usage dropped by 30%, while yield increased by 15% compared to manual methods. Farmers reports improved continuously in consistency in crop quality and reduced labor for routine monitoring. Future enhancements and Research restrictions. Integrating AI models to predict pest outbreaks or optimize harvest timing based on historical and weather data. Using drones for aerial imaging to detect plant stress or monitor large fields efficiently. Edge computing allows faster decision making by processing data locally interested of railing solely on the cloud. Open APIs would enable third-party developers to build pulsing for specialized crop or re- regional needs. Thank you, ma'am.